So the exponential population model, we talked about population a little bit yesterday on the notes from yesterday, and we saw that Columbus, Ohio, and Blake, and actually I continued to use Blake throughout the other classes, saw that it was actually very accurate to what we saw the population to be in whatever year that it was estimated to be. Population is used, one of the most popular ways in which we use exponential functions, okay? And so therefore, we're going to spend a little bit of time of looking exactly and tearing apart our basic exponential function and looking at how we can apply it with a population model. So we know that our basic exponential model is y equals, or I should say f of x equals a times b to the x. We are not straying from that whatsoever. We're not learning anything new. The difference is we're replacing the variables. They're going to be called something different. So in a population model, we have a population changing at a constant percentage rate. And I think that it was Caleb that actually made the comment yesterday also, saying, well, that had to increase at a fairly constant rate. And that's a really good thing to recognize that, you know, again, we talked about Quincy's population rate was pretty stagnant. But Columbus, Ohio, as it was increasing at a fairly constant rate, and it held true. So that's why it says that we're going to assume a constant rate of change on that. And then we have a new model. Well, I shouldn't say new, but just written in different, with using our different variables. So we have a population P at time t. That's what the t stands for. So population at time t is, P is our initial population. So that is what we know as A. Okay? So P sub 0 is the initial population. Anything sub 0 is always initial. So this is my initial population, just like what we saw with Columbus, Ohio yesterday. I think that was 632. And then our base has turned into something that in parentheses, and this is where we're going to kind of settle today, is in this 1 plus R. We know this as base. Give me the more formal name of the base. That is also called the growth what? The growth or decay factor, okay? The growth factor. And so knowing that this growth factor can be split into 1 plus a rate. All raised, and that's so tiny to see, but I hope your eyes are better than mine, that is a little t, okay? That's where the x should be, is a time t. Where P is the initial population, we just talked about that. R is expressed as a decimal, that's why we did our previous little warm-up. And T is in time of years. So understand, if there's one thing that you're going to get out of this lesson, okay, hopefully there's plenty, but our growth factor is 1 plus rate. That may seem so simplistic to you, but as we move forward, I don't want you to skip this step, okay? I don't want you to skip this step of recognizing that the growth factor is 1 plus rate, because from here on out, we're going to be given the rate, we need to find the growth factor. We're going to be given the growth factor, we need to find the rate. This always will be 1. And that is where, when we were doing a single multiplication, basically where that 1 is as well, okay? That means that entire thing, but then we're adding a rate to it, okay? So from here on out, it's all examples, okay? We're looking at just different examples that we can use the exponential functions with. So here we need to tell whether the population model is exponential growth or decay, and then we need to find the constant rate. Okay, so we need to find R, whether in the growth factor or in the decay factor. So let's look at San Jose. And here it's given for us. That was our initial population when they first started to look at the set of data. What's this 1.0136 called? That's my growth factor, decay factor. And looking at that alone, is it a growth or decay function? This is a growth function. Now, I want to find the rate. Okay, I want to find the rate. So I'm going to set my growth factor, because I know the growth factor is equal to 1 plus the rate. So I'm going to set that factor equal to 1 plus R. Okay, so that's my growth factor, and I'm going to set it equal to 1 plus r. What do I do to both sides? Subtract 1. So my rate ends up to be 0.0136. I want to represent that because it's asking what is the rate, and I don't say, oh, the rate is 0.0136. I represent that as a percentage, and what's the percent then? 1.36, move the decimal place twice. Great place for error. We just move that decimal place twice, and don't forget that the zeros are as important as any of the other numbers in there. Okay? So 1.36% is my rate of this growth function. Yes?
Is the t supposed to be an exponent?
Thank you. That is a misprint. That is a misprint. I caught that first hour. So yes, that should be an exponent. That's exactly right. That is a misprint on there. Okay? All right, so now let's look at Detroit. Do I have a growth or decay?
Decay.
How'd you find that as a decay?
It's less than 1.
It's less than 1. Okay? So I'm going to take my growth factor, which is 0.9858, set that equal to 1 plus r. What do I do to both sides? Subtract 1. Notice that is a negative 1. Negative 0.0142. So therefore, writing that as a percent, negative 1.42%. And does the negative out in front, does that make sense that would represent decay? Okay, so a lot of times you might hear somebody calling it still a growth rate. I have a growth rate of negative 1.42%. That's allowed. I have a decay rate of 1.42%. That is allowed. You almost get a double negative if you say that I have a decay rate of negative 1.42%. So you can say I've got a growth rate of negative 1.42, or I have a decay of 1.42%, but you almost get a double negative in there if you say I have a decay of negative, okay? I'm not going to get too hung up on that as you write that, but just understand that those are all different ways in which you'll see that written and spoken. All right, so now we're going to find our exponential function given this information down below. So we want to determine the exponential function with the initial value of 10, increasing at a rate of 5% per year. This is very generic, not necessarily associated with population or anything in specific, just very, very generic, getting us in the habit of being able to write out an exponential function given a rate rather than a growth factor. All right, so I know that my initial function, a times, and I'm going to write it as 1 plus r raised to some time. Change that to a time. F of t equals a times 1 plus r to the time. Or you could have x and x, doesn't matter. So when my initial value is 10, and let's come over here to this 5%. And I'm just going to do some work over here since this is our first one. Our rate is 5%. Converting that to a decimal, and I know that my growth factor equals 1 plus the rate, right? So that's going to be 1 plus 0.05. So what goes inside my parentheses over here? 1.05. Okay, and that's all we wanted here. just showing you how I can rewrite, given this basic information, how I'm going to write that exponential function. Okay, questions on front page? Yes. Okay, flip to the back. Bacterial growth. Something you guys have, if you've taken biology, probably have done quite a bit of as far as looking at bacteria that doubles, bacteria that or different bacteria that even have a half-life and that type of stuff. In fact, for right now, we're not going to be talking about half-lives. But if we did, this is the section in which it would come right here. Okay. How many of you have seen or talked about half-lives? Have heard of that? A few of you. Okay. But that's where this would come. And but here we've got a culture of 200 bacteria put into a petri dish. Culture doubles every hour. Predict when the number of bacteria will be 350,000. This is similar to what we did yesterday with the population of Columbus. Now, something I want you to look at, this is not in your book, and I just found this, very bottom of your paper, your notes. It says that note the growth or decay, I'm not sure what rate is, but I'm sure it's supposed to mean rate, is typically a percentage, but when it's in the formula, it's a decimal. The growth or decay factor is the actual factor if the rate is converted into a decimal and added or subtracted from 1. So this is not anything that we're going to be, anything that we need to solve. This is just FYI for your information. And hopefully it will help you. So up here it talks about the culture doubling. So I go down here and I see words in the problem. I see something that doubles. That means that my rate is going to be 100%. Well, where the heck did that come from? Knowing that it's a growth, where there's the 1 plus the 1, so actually then my growth factor becomes 2. So the growth factor of 2 actually makes a little sense if it's doubling, but the rate of 100%, this just kind of gives you an idea of where that comes from and the different words that you may see in some of your application problems that you're going to have. Okay? So this is just an FYI down below here. So with that, we have a culture of bacteria in a petri dish. What are we starting with? Okay, y equals a times b to the x. I'm really not going to worry about 1 plus the rate unless it specifically tells me something that I need as far as rate. This does not say anything here about pulling out what is the rate. It's just wanting to know when is the bacteria going to be 350,000. This is very similar to our problem that we had yesterday. So y equals, what's my initial value? When did they start counting the bacteria? At 200. What's my growth factor? 2. Doubles, and again, if that's confusing, refer to your chart down below. And that also, when we were looking at our financial situations, if we invest $1 at 100%, that would be awesome. What am I going to end up with at the end of the year? $2. Okay? So this is basically what we're talking. It doubles. Okay? So if I invest $2, how much am I going to have at the end of the year? 4. If I invest 4, I will have 8. Okay? So that's where the doubling comes from here. All right? To some time. I don't know what that's going to be. So this is going to be strictly guessing and checking. Okay? Strictly guessing and checking what we had done yesterday. What's another method besides just guess and check that you could do? You could graph it. Absolutely. Absolutely. Now, I'm going to make this a little competition. I had somebody in first hour, and she sent me a picture of it via Remind, because we kind of ran out of some time on it, to where she got it so close to 350,000. And I want to see who in here can get it as close to 350,000 as you possibly can. And know that your exponent can be written in decimal form as well. Okay? So take a couple minutes and work this